So thank you. I appreciate the invitation to speak to this august crowd. So obviously, I can't tell you everything about experimental QCD. So I'm going to talk about a journey from deconfinement to confinement. I will start out with just a couple slides about the distribution of quarks and gluons inside nucleons and nuclei. And then I'm going to spend most of my time talking about the many-body physics of QCD. I study quark-gluon plasma, so I'll talk to you about its properties and how we know, and what are the interactions inside the quark-gluon plasma. I'll talk a bit also about the QCD shower evolution, which are things that we have heard about how to calculate, so I'll show you what some of those things actually look like. And then lastly, an interesting question of how do the hadrons actually emerge from quarks and gluons. So the starting point would be two different views of what's inside a nucleon. On the left, you see the theorist's view, which you heard all about from Raju. On the right, you see the experimenter's view, which you also heard about from Raju. What, of course, you want to see here is that you have the valence quarks, whose distribution peaks at a little bit less than x of a third, as you would expect. And then as you go to smaller and smaller x, you run across these nice wee partons. And in fact, you see there's a huge rise in the small x gluons. And of course, lots of QQ bar pairs. So that's what's inside a nucleon. Now, how about inside a nucleus, where, as we heard, you have an overlap in the distributions of the partons inside individual nucleons? And indeed, the gluon distributions from the neighboring nucleons overlap. And that gives an interesting modification to the plot I just showed you. You have the EMC effect, which moves things around to smaller x. At very small x, you have shadowing due to recombination of very small x gluons, and then an anti-shadowing region where the things that get moved around end up. And here's a somewhat historical picture of the ratio of the gluon distributions in nuclei compared to nucleons. This is the gluon distribution. Well, actually, it's the gluon distribution in lead. And gray is what was known in 2017. And you can see exactly this kind of shape as in the cartoon. The difference is as you go up in Q squared and different beam combinations that we will have at the electron-ion collider. And you can see that once you get to Q squared of about 10, the electron-ion collider will have a significant impact in what are the interactions of the overlapping gluon distributions. So we know quite a bit already. We're learning much more from the LHC than you see in this picture. But that's, of course, very important in understanding the interactions among the gluons. So next step is having measured from deep inelastic scattering where the quarks and gluons are in nuclei, you'd like to make QCD matter. To do that, we collide heavy ions at both RIC and the LHC. And this is what the events look like. They look like pretty pictures, but they're actually event displays. And yes, we can make sense out of them. Now, why did we want to make QCD matter? And why do we still want to make QCD matter? Well, the simple argument is from asymptotic freedom. If you have collisions where you make many secondary quarks and gluons, the average distance gets small. They're no longer confined. And if you don't believe me, you can believe this nice calculation from the lattice here that shows how the confining potential is screened ever more as you go up to higher and higher temperature. And the lattice tells us that there's a critical temperature of about 150 MeV, beyond which you should have deconfined quark matter. And that, of course, is what we were setting out to find when we first started working at RIC. We now have enough data that we can actually do some work here on the phase diagram of QCD. You've probably seen this many times. We're pretty familiar with the physics here of nuclear matter, so at very low temperature and mu baryon near the proton mass. At RIC and the LHC, we come into the phase diagram here from high temperature and low mu B, eventually making our way over here. We know from the lattice that at low mu B, there should be a crossover rather than a first-order phase transition. It is expected that perhaps there is a first-order phase transition at higher baryon density. So far, there is no crisp experimental evidence of that. If it is true, then there should be a critical point between the first and second order phase transition, and there's a lot of experimental work going on to look for that. I'm not going to talk about that today, but your local experimenters will be happy to tell you, or I can show you some plots at lunch tomorrow if you like. And you can see here some of the experimental facilities where those critical point searches are taking place. But I'm interested in the properties of the plasma, things which are maybe more easily calculated in QCD. So you saw those complex pictures, and you may have been wondering, how can those crazy experimentalists make any sense at all out of those very heavy-looking events? So, of course, what we do is we study the quark-gluon plasma with particles, and we look transverse to the beam at 90 degrees at mid-rapidity, because that's where the temperature and density should be the maximum. You can look at relatively low momentum particles below about 2 GeV. That's the thermal emissions from the quark-gluon plasma, or what the plasma physicists would call internal plasma probes. And I'll show you some results from that. If you look at higher temperature, at higher PT, those then the process of producing those particles actually sets a scale other than the temperature of the plasma. And so you can think of this as an external plasma probe. It's, of course, auto-generated in the collision, as you can see from the cartoon here. You have a high momentum transfer scattering between incoming quarks or gluons, and then those things have to make their way out through the plasma. And that makes them an excellent probe. Now, of course, any decent experiment should have a control, and we do have a nice control probe, photons, also W and Z bosons. Since they don't participate in the strong interaction, they should not be affected by the quark-gluon plasma, and I will show you in a moment that indeed they're not. So the first thing we did after we turned on RIC, so there is a historical component to my talk. I'll give that first. We looked for collective behavior. Now, how do you do that in such a complex and short-lived system? Well, as you can see, oops, let's see here. As you can see in this cartoon, this is what happens just immediately after a heavy ion collision at some finite non-zero impact parameter. You can see the remnants of the beam heading off at the speed of light. And in this interaction, in this overlap region, you have a kind of almond shape. You can see that better if you take the beam's eye view over here. And so you have an asymmetry in coordinate space. Now, of course, there are a lot of interactions among the produced particles, and those translate the asymmetry in coordinate space into an anisotropy in momentum space. If there is collective flow, then you can measure that anisotropy in momentum space, and we do that. The way we do it is by looking at the opening angle difference of all of the particles that come out at mid-rapidity, and if there's no preferred direction, in other words, if this initial shape doesn't matter, then you would expect the opening angle distribution to be flat. As you can see from these ancient data over here, that's definitely not the case. So what we do, we measure this, and then we subject it to a Fourier analysis. And the second Fourier component essentially measures the amplitude of this modulation, and that tells us the anisotropy in momentum space. And so you often will see heavy ion talks presenting the value of what we call V2. It's just the second Fourier component of this distribution. So if you look at the magnitude of this anisotropy here, the V2 value in the black and the blue points, they're plotted going from very peripheral or grazing collisions to very head-on or central collisions. Of course, when you have a perfectly head-on collision, there is no initial asymmetry, so there shouldn't be any final state anisotropy, and there isn't much. It's not quite zero, because B is never exactly zero. But you can see that the values here are really quite big. It's 5, 6, 7, 8%. That's actually a huge anisotropy compared to what we expected. The fact that we see that as a final state correlation tells us that we had a very large and very fast pressure buildup. So the next thing, of course, you would do is to ask, does hydrodynamics work? Well, these red bars over here are actually very early calculations with perfect hydrodynamics, so no viscosity whatsoever. And you can see that they actually did a not too bad job in those early data. I need to break briefly and tell you an amusing story. So in the very early days of RIC, at Stony Brook, we had theorists and experimenters, and we weren't supposed to show each other our stuff. But late at night, the students did, the students and the postdocs, and they actually made the very first version of this plot, and everybody was extremely excited, as you can imagine. You can look as a function of the transverse momentum separately at pions and protons, and you can see that the red calculation with hydro actually does a pretty reasonable job. This was one of our first, probably the first evidence that we really were making a quark gluon plasma. And the reason for that is if you do the hydrodynamics calculation with a purely hadronic equation of state, you cannot reproduce the measured flow. And interestingly enough, you cannot reproduce the measured flow unless you have a very low viscosity to entropy ratio. It's the equivalent of the viscosity per particle. And that was the reason that the quark gluon plasma is often called the perfect liquid. And from personal experience and looking at both, I can tell you it's almost as perfect as vodka. But anyway, of course, these are very early calculations. I'm showing you in the preceding, in the intervening 20 years, there have been a lot of advances in relativistic viscous hydrodynamics. And you can actually see some evidence of that in this plot. There's also been a lot of improvements in the data. What you see here is, again, the opening angle distribution between particles. This was measured by Atlas in lead-lead collisions. They're supercentral lead-lead collisions, the top, most central 1% of the cross-section. And you can see these black points are, you see lots and lots of modulation. The Fourier analysis of that actually can give you values for not just V2, but all the way up to V5. Using this kind of data, and you can see the precision now of the identified particle flow, the V2, the error bars are extremely tiny unless you're looking at the phi meson. So by using these data to constrain hydrodynamical descriptions of the evolution, and you can see there are a number of different models, we actually have a pretty good idea of the shear viscosity and the temperature dependence of the shear viscosity. You also see some evidence of a bulk viscosity very near Tc. So it's interesting actually to compare this perfect fluid to other fluids. And we always think of liquid helium as one of the best superfluids. In fact, it is surpassed in superfluidity by ultra-cold atoms, where you can excite a Feshbach resonance, and the quark gluon plasma, which has an even lower shear viscosity per particle. And if you want to know what the string theory limit is all about, ask Sun. So what did we see? From constraining hydrodynamics with data, we saw that we have this nearly perfect liquid behavior of the quark gluon plasma. We know that the partons are deconfined. They don't behave as hadrons, at least not in the early time. But it is something to note that alpha S is not so small at that point. And so it is that interaction that makes the fluid strongly coupled or strongly correlated, depending on the language you wish to use. Now, as I alluded to in the previous slide, there are many other kinds of strongly coupled matter. Turns out that the rings of Saturn are actually dusty plasmas. Dusty plasmas and warm dense plasmas have liquid phases. They even have crystalline phases. The physics of the warm dense plasma is actually one of the reasons that NIF had to work so hard in order to achieve ignition, because unless they got a perfectly symmetric compression of their inside their hole round, then their plasma would kind of take off and not stick around long enough to generate much energy. I already mentioned the ultra-cold atoms. These are pictures actually taken of the elliptic flow that you get in a lithium atomic gas at 10 to the minus 7th Kelvin when you make it strongly coupled by exciting the Feshbach resonance. Exactly the same physics as we see at a lot higher temperature. And in condensed, strongly correlated condensed matter, you also have interesting phase transitions and nice superconductors. And in all of these cases, there's common physics. Again, you theorists know this much better than I do. There's a competition between attractive forces and then either repulsive forces or kinetic energy of the particles, as we have in the quark-gluon plasma. And so that competition means that we're dealing with many-body interactions rather than just pairwise interactions, which makes it really interesting. So now let me tell you a little bit about what we've learned about the interactions inside the plasma. So as I mentioned, we'd like to use the higher PT particles to probe the plasma. The beauty of those, of course, is that this initial hard scattering can be quite nicely calculated with perturbative QCD. And if you don't believe me, have a look at this spectrum right here. This is a spectrum of neutral pions and proton-proton collisions at root S of 200 GeV, taken at RIC. The lines are next to leading order calculations with two different fragmentation functions. And you can see that they reproduce the data very nicely, which is nice, because that means we have a well-calibrated probe. So having measured the proton-proton collisions, we can now look at head-on lead-lead collisions. Using a Glauber model of the nucleus, of a lead nucleus, we can calculate that a head-on collision with the cross-section we measure corresponds to about 975 nucleon-nucleon collisions. So we take this proton-proton data, scale it up by 975, and then compare it to what we measured in lead-lead in red. And you immediately see that there is a deficit. Take the ratio of those two, and we have the nuclear modification factor, which we normally write as RAA. So that ratio is shown here in the black points. And you see that you get out only a fifth as many high PT, well, sort of high PT pi zeros compared to what you expect from proton-proton collisions. And this is known as jet quenching, and it was predicted a long time ago by Xinyan, and I'm sure he'll tell us more about it on Friday. What you can see here also is that the eta is just as suppressed as the pi zero, and importantly, you see that the photons are not suppressed, as they should not be. So that means we know what we're doing, we know how to handle the geometry, and now we can scratch our heads about why this, where did that factor of 5 come from? Well, of course, there's additional gluon radiation that's induced by interactions of your quark or gluon as it makes its way through the plasma. You can look at the LHC to much higher PT than the 20 GeV or so I showed you from RIC. The blue points here are charged particles, primarily pions, up to 100 GeV, and you see that even at 100 GeV, they're suppressed by a factor of 2. And if you look at jets out to 300 GeV, you continue to see this factor of 2 jet quenching. And again, the control of photons, Ws and Zs, those are not suppressed. Now we can do a little bit better than this, actually a lot better than this. The first step is to look at the jets, and in particular, use dijets in order to see what happens to the pair of jets. So when you trigger on a 200 GeV jet, this one's actually 205 GeV measured by CMS, you preferentially are going to get that out of the surface of your quark-gluon plasma, and that forces its partner to make its way through the longest path of plasma that's possible. And then you can see the opposing jet is not 205 GeV as it should have been, but rather 70 GeV and rather spread out compared to its partner. We know from changing the energy at RIC that the suppression, the jet quenching, sets in somewhere between 27 and 39 GeV. We don't know exactly where, because you have some enhancement in the low PT particles due to the nuclear structure, and you have then the jet quenching, but it's somewhere in that range. We had a very interesting surprise as we were looking at the jet quenching, and that surprise was that the heavy quarks also lose energy and flow. If you look here on the left, this is the RAA measured by CMS as a function of PT up to 100 GeV. The grayish points are the charged hadrons, and if you look carefully, you see these green points, that's d mesons. So the charm quark is just as suppressed as the light quarks and gluons. The red points here are the decays from B hadrons, and you can see those are also suppressed, although not quite as much. Then if you ask, does charm flow, you can see here in these black data points that, again, the V2 is quite substantial. Here at 434 GeV, it's as much as 20%. So it flows just as much as the light particles do. All these nice colored lines are, again, different models with different ways of handling the radiation and the collisions. And you can see that they can reproduce the data reasonably well. Now, induced radiation you expect, collisions are great. Of course, one would naturally ask, collisions with what? Maybe it's thermal, gluons with a thermal mass. Maybe it is collisions with some many-body system in there. And so naturally one can ask, what is the drag force of the strongly coupled plasma on a moving heavy quark? And by using these models, all these colorful splotches and lines here, we can actually extract, by constraining those with the data and then looking under the hood, that the diffusion constant for heavy quarks is somewhere between 1.5 and 4.5 near TC. So the interesting question now is how to connect the observations to QCD. Well, a very nice way to do that is to use jets. So I have this cartoon I'm extremely fond of. We've heard a lot about jets already in the last few days. We know that there's a shower, a parton shower, which is calculable perturbatively. Of course, if you place your jet inside quark-gluon plasma, then the primary parton and the shower partons will interact within the plasma, and you'll get a medium-induced gluon cascade, which will tend to spread the energy out over a larger radius. Of course, the plasma is finite in size and lifetime, and so eventually you come back to an in-medium parton shower, and it hadronizes, and we collect that into the jets that I showed you here that you visually see in this nice calorimeter data. So let's use jets to see what's going on. The first thing you might do is use a photon or Z-tag jet and see how much is the energy imbalance. What I showed you before was just how many jets of any particular PT, how many particles do you see compared to how many you expected. Now we can actually see how the energy moves around. So what you see here on the left is a gamma jet event, and here is this one's gamma jet, this one is Z jet. In green here and in blue here is the measurement in PP collisions of the yield as a function of the jet PT over the boson PT. And you can see that here in Atlas it's peaked at about 1. Here for the Z jet it's peaked at about 0.9. And if you're wondering why they aren't both exactly peaked at 1, it's because of how the measurement is done, what's missing, and the size of the jet radius you use. So you can think of the pp as the calibration. Now, if you look at the red points on both sides, you see that in lead-lead collisions, that distribution is shifted down. So the jet you observe carries a smaller fraction of the boson's energy, just as you would expect if you have jet quenching. We can look inside the jet, and this is a beautiful measurement from Atlas, where they took jets of a radius parameter of 0.4, and then they looked at the particles inside as a function of the radius, the distance from the jet axis. So you can think of it as circles being drawn around the jet axis. Black are just about on the jet axis, and you see in the ratio of lead-lead to pp, no modification. However, as you look further and further away from the jet axis, you do see a modification. You see a suppression of the higher PT jet fragments, and you see an excess of the softer jet fragments, which is exactly what you would expect from the cartoon I just showed you. So you see it's not crazy. Yeah. This, in effect, means that at large jet radius, you see a broadening and lots of soft stuff, and the PT distribution inside the jet would appear to be narrowed. I love this data. At least I used to love this data. The problem is that all of you guys tell me, well, it's uncalculable. So we need to measure something. We need to pick an observable that is also useful from the theoretical point of view. And so that's why we look at jet substructure. There we really can compare to perturbative calculations and find observables that avoid various ugly singularities and don't require you to put in some phenomenological fragmentation function. And so here's a list of various observables. We can also groom the jets to remove the underlying event because, as you might imagine, with such a complicated event, there's a lot of stuff going on, a lot of soft stuff from the plasma, and that can confuse one's jet substructure if you don't pick the right one. And so you can groom the jet to get rid of those. And of course, we also compare the jets from light quarks and heavy quarks. There's lots and lots of substructure data. I don't really have time to go through it today, but I do want to just point out that for Torbjörn, I put here the experimental measurement of the Lund plane, so we can talk about that. Yes, we can measure it. Now, what I do want to talk about on the subject of jet substructure is something that George actually asked us to do, and he asked us yesterday, and lo and behold, we did it. So, okay, maybe it was a little bit of a setup, but anyway, let's talk about energy-energy correlators. So, you heard about them a little bit already. You will hear about them a lot more from Ian Molt. The idea of the energy-energy correlator is to look at the correlators, the correlation of your energy flow operators. And then you can integrate that as a function of the distance between them. Experimentally, this is actually not so hard to measure. Why? Well, what do? We find a jet. We then sum over all of the hadron pairs inside the jet, and you count the pairs. You count the pairs with a weight. And so we weight each pair by the product of the PT of the two particles in the pair divided by the PT squared of the jet. And so it's really just a weighted two-particle correlation function. And we experimentalists have a lot of experience with measuring two-particle correlation functions. You can do this with calorimeters also. And so you'll probably will see on Friday some energy-energy correlators measured calorimetrically by CMS. There, it's not exactly particles because there's some overlap in hadronic calorimeters, but the idea is still pretty much the same. So what we've done is we've actually looked inside the jets, and you may notice that I snuck away from a somewhat historical story to something that was done. Okay, it wasn't done last night, but it was done about 2 months ago, so it's pretty new. So after reconstructing the jet, you can see, as you see in this nice cartoon here, you've got some hadrons inside. And so you look at every possible pair combination, and then you plot you plot that pair as a function of the angular distance between them. And as you can kind of see in this cartoon, when the PT is higher, that's going to give a higher weight. So the pairs where both PTs are large, those have a larger weight than these guys here, where the PT values of your two hadrons are smaller. And that's actually extremely useful because that suppresses the soft contributions, suppresses underlying event. It suppresses the non-perturbative effects that are very difficult to calculate and understand. So we don't have to groom these jets. Okay, so what does the data look like? So what the data tell us, what's plotted here now is the energy-energy correlators measured in 5 TeV proton-proton collisions by Alice. These are all tracks above 1 GeV inside a jet with a radius parameter of 0.4. We have 3 different jet energies, 20 to 40, 40 to 60, 60 to 80. And you might wonder why such soft jets. Well, there's 2 reasons. One reason is practical. Alice is not a high-rate experiment, and so we run out of statistics above 100 GeV. But there's actually another reason, and that is that we're interested to use this to ultimately probe the quark-gluon plasma. A 100 GeV jet does most of its fragmenting outside the plasma, whereas a 20 or 30 GeV jet does a lot more fragmenting inside the plasma, and therefore is a better probe of how the plasma rearranges the particles inside. Okay, so this side over here at large angular distance, that corresponds to early times. As you go to smaller angular distance, you decrease the energy scale, and you increase the time of when that interaction took place that gave you the pair. So let's now have a look more closely. The early times are the parton cascade, and so that should be calculable perturbatively. And we have now here a very nice yellow line from Kyle Lee, who's sitting in the back, shaking his head. And that's a next to leading log calculation, and he gets the shape just bang on. On the late time side, the purple line is what you would expect this energy correlator to look like just from free hadron scaling. So just free hadrons. And that also works reasonably well. And there's this very interesting range here in between when nature makes the transition between partons and hadrons. When does that happen? Well, it happens as the virtuality approaches lambda QCD. Now, interesting question is where do you want to look? The peak is an obvious place to look. And I'll tell you a little bit more about that in the next slide. But I think it's also interesting to measure where is the place where we deviate from the perturbative calculation. And it's early days. I can't yet tell you exactly what we learned from that. Here's what the data look like for our 3 jet energies. And you can see here the ratio of the theory over the data. You can see the perturbative part does reasonably well. It's not perfect, but it's pretty good. And you can see sort of where you start to deviate from free hadrons. So I think we're getting at a tool to study the transition region. You can check for scaling. We have 3 different jet energies, as shown here on the left. Now, since the virtuality is given by PT times RL, you can scale these guys, multiply them by PT, and then you get this middle plot where you see that now all of the curves, in fact, line up quite well. The peaks line up. The integrals are not quite the same because it's normalized per jet. And of course, different jet energies have different numbers of particles. So if you area normalize them, you can compare the shapes of these quite well. And lo and behold, you find that, in fact, there is a completely common shape. The width of this distribution, the half width is 1.8 GeV. And the peaks all line up here at 2.4 GeV PT times RL. So my question to this haloid group is, what's magic about 2.4 GeV? I think it's trying to tell us something, but I don't understand its language, at least not yet. So we need some help with that. Now we can compare the data to the models. We heard quite a lot yesterday about Pythia and Herwig. And so the top set of plots are, again, the 3 different jet energies compared to Pythia and Herwig. And when you first look, you say, oh, gee, the models do pretty well. Well, the models should do pretty well because they all use fragmentation functions tuned to the data. So that's good, right? But by looking at the ratio of the models to the data here, you can actually see that there are differences at the 5 to 10% level. So they do pretty good, but not great. And if you look at these closely, you find out that Herwig actually agrees better with the data than Pythia does. And that's actually important. We'll come back to that in a moment. And if you look at the blue curve, you say, well, even though Herwig is better, it doesn't actually fully represent the data. The data are broader. So I'm going to come back to that, but first I want to show you some 3-point energy correlators. You do the exact same kind of measurement, except you take triplets and you plot the, you calculate the weight using the PT of all 3 particles, PT of the jet cubed, and you plot that as a function of the longest angular distance. And this is nice because then you can access higher order QCD splittings, so things that are still calculable, maybe better calculable. And if you make the triplet to 2-particle correlator ratio, you cancel out a lot of the non-perturbative effects and a lot of the systematic uncertainties in the measurement. And so you can see here, which I'm sure you're going to see from Ian, you can see that there's a nice sensitivity actually to alpha S. So here's what the data look like, this time in 13 TeV-PP collisions. These are the 3-point correlators. They look, generally similar in shape. And on the right side, you see the ratio of the 3-point correlators to the 2-point correlators. And what you see here is the hadron scaling, the free hadron scaling region is pretty flat, and they're all about the same. In the perturbative side, they're not all exactly the same. You expect that ratio to be proportional to alpha S and the log of RL. And the slope is what's sensitive to alpha S. And what you can see is that over here on the right-hand side, the higher the jet PT, the smaller the alpha S and the flatter the slope. And so by reading that off, we actually have another way to measure alpha S. So that's exciting. Well, I think it's exciting. I like to measure stuff. I want to come back to the question of how do the partons become hadrons. I showed you that the data in this transition region, they don't like Pythia very much. They like Herwig better, and they're still wider than Herwig. So I think we have something to learn from the hadronization mechanisms inside the different models. So as we heard yesterday in lots of nice detail, Pythia produces particles by string breaking, and the flavor correlations are actually carried on the string. In the case of Herwig, there's a cluster hadronization. So first, the locally connected partons are collected into clusters, and then those clusters decay into the hadrons. And physically, this step must take longer, thereby making that hadronization region somewhat wider, and that is actually what you see when you compare the 2 models. Now, in particle physics, I think most of the conversation about hadronization has focused on strings versus clusters. But we've actually seen something else in quark gluon plasma, and that is that the way that hadrons seem to form out of a quark gluon plasma is actually simpler. It's a statistical hadronization. And so you essentially are connecting partons which are nearby in phase space. And the reason that you should believe me when I say this, what you see here is the V2 per quark, so that collective flow, the second Fourier component, per quark in many different types of hadrons as a function of the transverse kinetic energy of the hadron, again, per quark. And then you see that the V2 curves all fall on a common curve. And it turns out you can exactly reproduce this if you just assume that the hadronization takes place by a recombination from a thermal distribution. And there are lots of papers about this. And it works for lots of things. We find that if you count J psi's as a function of square root of S of the collisions, you also see some evidence that you have final state J psi recombination from a thermal distribution. So this is another way so maybe hadronization is actually just filling a phase space. So let me go back to looking at the data here. As I said, the data are somewhat broader than Herwig, and a longer time than is going to be needed to form the hadrons, right? Very good. So I just want to end by pointing out that we're excited about the electron-ion collider. It's going to be the new QCD machine in approximately 10 years if we're lucky. How is this going to be done? I mean, you heard some beautiful information about the physics that can be done with this. I'm very excited about that. It's going to be built by essentially adding an electron ring to the hadrons at RIC. Makes a lot of sense. And the kinematic range that will be opened up is shown here in this gray area. Of course, a lot of information at very small x is being gained from the LHC, especially jets at the LHC, and those are, of course, quite high Q squared. So adding the DIS with electrons on nucleons at the EIC will fill in a lot of space. And of course, for electrons on nuclei, there's a lot of terra incognita. So let me summarize.
So the range for the electron-ion collider wasn't visible on your slide.
Oh.
On the screen it didn't.
Oh no. All right. Oh, look at that. When I checked the slides, I didn't get this far. I was wondering why you guys were muttering. So it's a line that's above here. It's about like that. So you got a chunk above. Yeah. So it goes up to about that. Yeah. Good. Thanks for telling me. All right. So summary. First point I want to make is experimental QCD really is a thing. I know when people saw my title, it was probably ha ha ha, but there's a lot we are learning about QCD from experiment. Summarizing what I think I told you today, the binding rearranges the partons inside nucleons, as you would expect. Interesting philosophical conversation to be had is, do the neutrons and protons maintain their isospin in there? Well, I don't know. That maybe, maybe at very small x they don't. I don't know. We've seen a lot of very interesting many-body QCD in quark gluon plasma, which flows hydrodynamically with a very low viscosity. It has a number of features that arise from the strong coupling, including the viscosity and the opacity that gives us the jet quenching. I showed you how the heavy quarks are stopped, flow along with the matter. I showed you how we can look inside jets and see QCD at work. That's interesting in PP collisions, and of course there's a wealth of data from all the experiments at the LHC. And we see that the jet energy loss shifts fragments to a lower PT and a larger angle, just as you would expect. And the energy correlators give us a way to separate the perturbative part of what's going on from the purely confined hadronic physics. They suggest a longer hadronization time than you would get just from string breaking. And I think it's very cool that we have an old tool that we can now put to a new use and really start to pin down confinement. I did not mention, we also observe a dead cone for radiation off a heavy quark. This was something predicted a long time ago. I took it out of my slides, but I'm happy to show it if anybody asks. Thank you.
Yeah, thanks for a great talk. Questions?
Calibration and sensation. Frank Wilczek once wrote, yesterday's one is today's the other. Maybe we can go back to the first runs from Phoenix, from Rick. You showed some data, I guess, from run one. It was PP collisions. It says calibration. Let's compare the pion transverse momentums spectrum.
That was actually it
Run
was the
three.
second year of Rick running.
And
Yeah.
they published it so quick. Okay, it's Piero. How do we look at those plots and assess the significance of the agreement, or if it's, let's say there were a tension, so let's say there was a 5.3 sigma tension at 9.77 GeV over C. How would I see it in that plot? Which I think you can see in the 2005 longer paper.
Let's see. I think you were talking about
PP, the calibration.
this one.
It's good agreement. How do we know? When you look at this plot, what is it? How do you read that off? The last line, maybe?
You want to know, does that look good or not?
What are these lines, these error bars?
Okay, so these error bars, what you see here, these two lines are supposed to show you an error band, and that has in it experimental systematic uncertainties, but also the uncertainties that come from the calculation, which was done, in 2003, what cutoffs they used and so on.
Is that bump at 4 GeV, 3.3, and the last on the D? Is that bump? What is that here? Or is that at the bottom here in the data?
Yeah. But so what I want to show you is, it comes from the data. The data are now, of course, from the LHC. These are done in a way where you don't even see the uncertainty. And why am I not worried about that? I'm looking at a factor of 5. And so I'm not too worried about, these bumps and wiggles in the data at that point. Now, of course, if you could say, why didn't you use this to say, this is the right fragmentation function, right? And then you could say, well, okay, I'd like that one better. So, but at this point, we were not doing precision physics. And a lot of heavy ion physics, I fear, still is not precision physics. So Bob has a question. Oh, oops.
Barbara, thank you. On slide 31, when you were talking about the magic value of 2.4
Yes.
GeV,
Please tell me.
but for curious people who want to think about that, but you weren't very impressed with the number right above that. Is that obvious what this 1.8 GeV is?
It's a great question. Why didn't I jump up and down about that? Well, oops, wrong one, sorry. One more. Which one am I looking for? I apologize, I've gotten all confused here. Okay, so why am I not, all excited about I understand how this thing works. No. So the 1.8 half width at half max, that actually depends on more than just, where's the peak and how wide is it right around it. That depends on exactly what is the slope. Well, come on. It's supposed to find this guy. Yeah, well, all right. I can't make this guy work anymore. I confused it. So if you look at the right, you can see that the width depends not just on the peak itself, but on the, there we go. It depends also on the slopes of those tails. And, when we looked at the ratio, it's pretty good, but taking your question to heart, it's not that good. And so we don't know those slopes so well. So I'm not ready to ask you to make physics out of the 1.8. But that peak, why is it there? Why isn't it closer to lambda QCD? I don't know. I mean, there has been some speculation from my colleague Bernd Müller that maybe what matters there that sets the position of that peak is a glue ball mass, below which you're not going to radiate more gluons. Well, could be true. I don't know.
So it's like 5 times bigger than you would expect, at least.
Well, that's what I used to think, but I don't actually know what I should expect. So that's a question to all of you. Maybe Bob knows the answer. Oh, okay.
Thanks for a lovely talk. I wasn't surprised to see V2 not equal to 0, of course, but is the non-zero value for V3, V4, and V5 obvious? It wasn't obvious to me from the geometry of the collisions.
Right. Well, so, why are there higher harmonics? Well, if you assume that the nucleus is a bag with completely static nucleons, which are smoothly organized, then you would expect no V3. But in fact, we know that nucleons move around inside a nucleus. Furthermore, the quarks and gluons move around inside a nucleon. And if you include those fluctuations, and then you let your hydrodynamics go, you get V3 and V5. So those are really very sensitive to the internal structure of your colliding objects.
So you're learning anything new about the nucleus?
Interestingly, the answer is yes. I'm not an expert and not prepared to really discuss this, but actually these precision measurements of the higher harmonics do tell you some new things about nuclear structure. We heard about those at Quark Matter. They have some sensitivity to short-range correlations, for example, that are completely different from what you can do with electron scattering. And surprisingly, in some observables, quite competitive. Good.
Okay, let's thank Barbara again.